Hi everybody, happy Friday. This is lecture number 15. This is February 20th. We're discussing section 7.7, again, differential equations. We started this on Wednesday, and we'll discuss it again on Monday. That's 3 lectures in a row discussing differential equations. All right, first part of the meeting, I want to briefly recall exponential growth, which you studied last fall or whenever you had Calc 1. So a description of exponential growth is the rate of change of some quantity is proportional to the quantity. So that translates into mathematical jargon as the derivative of the quantity that, with respect to time is equal to k times the quantity. And then that solution can, that differential equation can be solved. And the solutions are of this form. Y as a function of t equals the constant y0 e to the kt. So y0 is the initial value. If you plug in 0 for time, you get y parentheses 0. So y at time 0 turns out to be that symbol, y0. Now, a couple of things to observe. First of all, this describes a situation where there are unlimited resources. So there's no inhibition to the growth. Another thing to observe is the constant function y equals 0 is a solution. Now remember, if you're presented with a differential equation and you're presented with a function that's a candidate to be a solution, you can always check to see if it is a solution. You check by putting the function into that equation and see if it works. So the left side is d dt of the number 0. That's going to be 0. And the right side is y0 e to the 0. That's, y0 is the initial value, which is the value all the time. So it's that. I'm sorry, go back to this. The right side of the differential equation is k times y. So k times 0 is the number 0. And so the left side equals the right side, so it is a solution. So again, to check that a given function is or is not a solution of a given differential equation, you just plug the function in and you go to work. I mean, we know how to solve this equation. The book actually presents a solution, but we also solved it in the fall. But if you're given the solution, a possible solution, just check it. Okay, meeting part 2. Is what we're going to spend the rest of the hour talking about, which is logistic growth. So in logistic growth, resources are limited. And so the environment can only support a population up to a certain size. So there's a maximum population that the environment can support. So a maximum population, which we're going to abbreviate with the letter M, that the environment can support. And this maximum population is called the carrying capacity. So that's a new thing. There's a constraint on the population. Okay, so a description of logistic growth is this: the rate of change of the population I could say quantity, but we're going to be mostly be interested in talking about populations, is proportional to it's proportional to the product of the population and the amount by which the population falls short of the carrying capacity. So the amount that the population falls short of the carrying capacity. So if we translate this into mathematical jargon, we get dy dt equals sum k times y times m minus y. So the rate of change of the population is proportional to the product of the population and the amount by which the population falls short of the carrying capacity. So recognize that as the kind of crazy differential equation that I presented on Wednesday. Now I want to make some observations. So on Wednesday I presented a function and I said this function I'm going to try to sell you as a solution to this differential equation. I didn't show you where that function came from, but I just presented this function and showed you how I could convince you that it was a solution. How? Well, I plugged that function into this equation and confirmed that it made the equation true. So in the book, the book develops that solution. They show where that solution came from. And I told you on Wednesday that I'm not going to do that in class because the book does it well. But I'm not even going to present that solution yet. I want to start by looking at this equation before we do any work. Oh, and I'm going to say here where k is a positive real number. So first of all, are there any constant solutions? Can anybody think of a function of the form y equals some constant that would be a solution to this equation? Marcy?
Y equals 0?
Yeah, so the constant function y of t equals 0 is a solution. So let's check that. The left side is, the derivative of 0 is 0. Okay, great. The right side. The right side is k times 0 times m minus 0. So K times 0 times M, so that's the number 0. Great, these match. All right. Can anybody spot any other constant solutions? I've already called on you, so Jason? M. So the constant function that's y of t equals m is also a solution. I think you can see if I plug this into the left side, the derivative of this is 0. If I plug this into the right side, I get k times m minus m. That's going to be 0. So the left and right sides match. Now, what scenarios do those correspond to? Well, remember, we were talking on Wednesday about bacteria, and we were pointing out that you all have bacteria cultures growing in your kitchen. Well, so Mary went home and scrubbed the heck out of her kitchen, so there's no bacteria anywhere in Mary's kitchen. So the population is 0. So the population will remain 0 forever because she did such a good job of cleaning. The other scenario when y of t equals m is, well, the population has reached kind of an equilibrium with its environment. That's the carrying capacity, and it's just going to stay there forever. All right. Some more observations. If the population is greater than 0 but is less than the carrying capacity, so y is some positive number, but it's not as big as m, then m minus y will be a positive number. So the derivative dy dt equals k times y times m minus y. We have positive, positive, positive. So the derivative is positive. If the derivative of a quantity is positive, what does that tell you about the quantity? Increasing. Fantastic. So will always be increasing. So let's think now about our possible solutions that we've observed. Here's one. Y of t equals 0. This is Mary's kitchen. And another one is this. And the other scenario is, well, I start with some initial population that's positive, but is not as big as the carrying capacity. So at some time 0, at time 0, we have some population y0. And it's not as big as m. M is up here somewhere. Well, the fact that the population has to always grow means that it has to always grow. So there we go. We're not sure how it looks, but it's got to go up. But it can't go beyond m, because m is the carrying capacity. So there's going to be some kind of asymptote. And you can see it's going to be an asymptote. It's not really going to get to m, because when y gets closer and closer to m, this quantity, m minus y, will get closer and closer to 0. That's going to cause dy dt to get closer and closer to 0. So the closer you get to that carrying capacity, the slower the growth is going to be. So the slope gets closer and closer to 0. So those are the three kinds of solutions we're noticing. Now, from the book, well, I'll set up an outline of the solution. We already know that y equals 0 is one solution. We know that y equals m is another solution. So we have dy dt equals k times y times m minus y. And off to the side, we observe, or I'm not going to say off to the side, I'm just going to say right here, observe y equals 0 and y equals m are solutions. So what we want to do is we want to look for some other solutions. Well, let's assume that y is not 0, and let's assume that y is not m, because we know what happens. If y is 0, then it just stays 0 forever. It's Mary's kitchen. If y equals m, then it stays m forever. That's my kitchen. There's a bunch of stuff growing in my kitchen, and it's reached equilibrium with me and my cats. All right, so look for other solutions. So we're going to assume that y is not 0 and assume that y is not m. Okay, well, if y is not equal to m, then m minus y is not equal to 0, so I can divide by it. So divide both sides by the product y m minus y. That's a non-zero number because I'm assuming that y is not 0, and I'm assuming that y is not equal to m. So I get on the left side 1 over the quantity y m minus y dy dt equals k. Okay, let's put this in differential form. So that kind of looks like multiplying both sides by dt, but it's not really that. But the differential form is 1 over the quantity y m minus y dy equals k dt. Let's integrate both sides. One over y m minus y, the integral of that, equals the integral of k dt. Look at that. That, my friends, is a partial fractions problem. You're going to have to use partial fractions to integrate that. So if you read the book, they do exactly that. They attack this integral using partial fractions. All right, so see the book for this work And the result is y as a function of time equals Cm over C plus the quantity m minus C e to the minus kmt, where C is a non-zero real number. So C is a number greater than or equal to 0. C could be 0. If C were 0, then this would just end up being y of t is 0. C can be positive, but we can't have C be negative. Okay, so let's make some observations about this. So again, on Wednesday, I presented this as a solution to that differential equation, and I did the grungy work of seeing what happens if I do the left side, if I take the derivative of that function. I got a mess. It was a mess. I wrote it down. And then I did the right side. I did all of this to that function, and I got a mess, and they were the same mess. And I realized, okay, so that is a solution. So Wednesday I showed you that this is a solution. But let's make some observations about it. So observations about y of t equals Cm over C plus m minus C e to the minus kmt. So the first observation is y parentheses 0. Well, let's plug 0 into that. So I'm going to get C times m over C plus m minus C e to the minus k m times 0. Oh, but that's e to the 0. This whole thing is 0. So what's e to the 0? That's the number 1. So this is going to be Cm over C plus m minus C. Oh, but the C's cancel. They have a party. So Cm over m. Oh, but the m's cancel. They have an m party. And you just get C. So that tells us the significance of that letter C. It can be any positive number, but the significance is it's the initial value. So C is y parentheses 0, which is also written y subscript 0. So I'm going to use that symbol instead of C. So we're going to rewrite y. Y of t equals y0 times capital M times y0 plus capital M minus y0 e to the minus kmt. All right, now what I'm going to do now in the book, they, as part of the deriving of the solution, they observe that constant has to be y0 somewhere in the derivation. So they actually don't write down, I don't think they write down that solution. Now, remember I just erased my beautiful graph. I said, what happens if you start with a population that's greater than 0, but it's not as big as the carrying capacity? Well, we reasoned that population had to grow because the derivative is positive, but it couldn't grow any bigger than the carrying capacity because you're going to run out of resources, and the differential equations showed that the growth would slow down the closer you got to the carrying capacity. Well, let's look at that function And let's take the limit as t goes to infinity and see if that's borne out in this function. So consider the long-term behavior. So the limit as t goes to infinity of y of t. That's going to be the limit as t goes to infinity of y0 m over y0 plus quantity m minus y0 e to the minus k m t. Okay, so this symbol tells us that t is getting huge and positive. That's because of that. T is going to infinity. So we're supposed to look at this and imagine what's going to happen with this when t gets more and more positive. So that means that minus kmt is getting huge and negative. So that stuff that's up there in that exponent is getting huge and negative. So raise your hand if you can tell me what is happening with this. E to that stuff.
Small and positive?
Yeah, so closer and closer to 0. Okay, so that whole term there is getting closer to 0. So that means that m minus y0 times e to the minus k mt is getting closer and closer to 0. So that means, let's skip ahead a couple of steps. So y0m over y0 plus m minus y0 e to the minus k mt. So that's y of t. Well, if this part of it's getting closer and closer to 0, that means this whole thing is getting closer and closer to y0 m over y0. Oh, but that's just the number m. So the limit as t goes to infinity of y of t is m, which is, again, the carrying capacity. So that's why we had, again, we had that graph. If you look up in your notes, there was a horizontal asymptote that started at population y0 at time 0, and then it grew and approached that dotted line y equals m. So the horizontal, so the graph has a horizontal asymptote at y equals m. Okay, there are all sorts of examples where misguided naturalists think they're going to bring some cute species to our country. Can somebody give me an example of some 19th century naturalist who, or earlier, that brought some species here? Marcy?
Not this country specifically, but I remember some guy brought a bunch of rabbits to Australia.
Ah, we know how that went, right? There's a movie. They made a movie, The Rabbit-Proof Fence. So it didn't go well. This country, I think starlings, wasn't there some dude who was in England and thought, oh, the starlings are so pretty, so they brought a couple of starlings over here? Say it again?
Sounds about right.
Yeah, okay. So, you know, all sorts of enthusiastic naturalists. You all might be. And of course, you know, the starlings have not devoured our country. You know, there's some kind of equilibrium. Not at least in my backyard, they devour a lot. But there's a kind of a stable population of starlings. So apparently there is some capacity, some carrying capacity for starlings in our country and for bunnies in Australia. But what happened early on when that naturalist brought that pair of bunnies to Australia in the early days? This comes under the heading of observations. What happens when the initial population, Y0, is much less than the carrying capacity? So when the dude steps off the boat in Australia with the breeding pair of bunnies. Let's look at that solution. Y0 m on top, Y0 plus m minus Y0, e to the minus k m t. Okay, so things that are big, I'm going to put a red circle around. This is huge. You've got the whole continent of Australia. But this is small. The initial, you know, the dude steps off the boat with a pair of bunnies. So this whole quantity is roughly m times that. You can ignore that m minus y0. Just make it m. And look at this. Initially, time is 0. So e to the 0 is the number 1. So this would be just the number m. This is huge. And this is small. Now, as time grows, this quantity starts to get smaller. But in the early days, when time is very close to 0, this quantity here, e to the minus kmt, is close to 1. So this thing is close to m. So this is roughly y0 m over m e to the minus kmt, right? Because I can ignore the small thing. Oh, but let's simplify that. The m's cancel. Y0 over e to the minus mkt. Can anybody think of how to simplify that? Dividing by e to the minus kmt. What if I wanted to eliminate that negative exponent? Bring it to the numerator. Y0 e to the m, or to the kmt. Realize what that is? That's exponential growth. So when the dude steps off the boat in Australia with his breeding pair of bunnies, there might be a limited carrying capacity on the continent of Australia. But early on, his bunnies don't behave that way. They just grow, their population just grows exponentially. And the bacteria that was in Mary's kitchen on Wednesday, you know, it might not have reached its carrying capacity. I can tell you it probably hasn't. You can see my house for a bacteria that has reached its carrying capacity. So in the early days, logistic growth can look like exponential growth if the initial population is much smaller than the carrying capacity. So let me go back. Let me draw this again. Remember the example where we have a carrying capacity that's way up here and an initial population that's way down here. And I said, okay, it's got to grow, but I didn't really know, and there are lots of ways it can grow. It can grow like this, it can grow like this, but now we realize, oh, it's got to grow like an exponential function, so it's got to be concave up for a while. Not level, it's not a parabola, but it's got to be concave up for a while, like an exponential function. But as the bunnies start to come up against the limits of the environment, they start to feel some limits on their growth. So logistic growth has this kind of snake-like behavior. And there's a cool book problem, I forget if it's assigned as homework, to show that the time at which the growth is the fastest is the time at which the population has reached half of the carrying capacity. It's really cool. And it kind of makes sense because if you look at this equation, dy dt equals k y m minus y, this part of it, so the derivative as a function of y would be a parabola facing down with with intercepts at y equals 0 and at y equals m. That parabola would have its peak at 1/2 m. Really cool. So there's all sorts of stuff. It's a real rabbit hole, these differential equations, because there's just so many cool things to observe about them. So I didn't get to an example that I wanted to get to of actually of a particular example with a population and a carrying capacity and an initial value, but there's nothing big there. It's just plugging numbers in, solving equations. See the book for examples of that. All right, so let's do our quiz.